Hello, my name's David McKittrick. I'm Outreach and Training Manager at a company called Blue Marble Geographics. We're a US-based mapping and GIS software company. And in this short presentation, I am going to ask and hopefully answer the question, got a drone, now what? Mapping with your UAV. I'm going to do with you a little bit of a presentation on a process whereby you can take drone collected data and transform it into geospatial data, map data essentially. But very specifically, we're going to look at 3D map data. We're going to recreate a 3D environment using an analysis process derived from simple drone collected images. Now, my objective is the transformation of overlapping drone collected images into a three-dimensional geospatial model of the target area using structure from motion. Now, this process, structure from motion, is an image analysis process. As you can see in the little screenshot on the left side, we're going to take multiple drone images, we're going to analyze them, we're going to look at features that are visible in each of those images. Now, because of the fact that we have this array of images, we're going to be able to see those features from multiple perspectives, and the underlying process involved in structure from motion is based on that idea that we're looking at a specific target area or specific target feature from those multiple perspectives. Similar to the way your eyes, because you have two eyes, are able to perceive depth. Having multiple perspectives, not just two perspectives, multiple perspectives, will give you that depth perspective. And the analysis is based on that premise, the idea that we're going to be able to see these features from multiple perspectives. So my objective in the next 10 minutes or so is to initially go through a few slides, but also to give you an actual real-world application of this. We'll take a look at the actual process and the end result. So what is structure from motion? Well, it's, as I mentioned, it's an image analysis process. We're taking these images, and you can see my crude little graphic on the left side, illustrating we have some drones floating up in the air collecting images, little squares representing photographs, identifying features on the ground, those black dots. And each of those black dots is being recognized and identified from multiple images, or within multiple images. And that is the underlying idea here. Now, in order for this to work, there's a few prerequisites. One of the important ones is that the image needs to know where it is to start with. What were the coordinates, or what was the location of that image relative to the other images? Also, what was the height? And that information is inherently derived from GPS. Images you capture are going to be geotagged, so that information is usually right in the image itself. The target area obviously needs to have features that are identifiable. This will not work with a flat plain surface such as a desert or water or snowfield. It's just not going to get the necessary texture. So in order for it to work, you need to have things that the photographs are able to identify. We need to have multiple images. Obviously just one image will not work, so we need to have multiple images to see those features from multiple perspectives with an overlap of at least 60%. Better, more is better in this case. And again, it's looking for those recurring patterns of pixels. It is analyzing the images, and derived from that analysis, it performs a simple process of triangulation to determine where that target area or that target feature is in three-dimensional space. I know where the image was captured from. I can determine based on mathematical process where each of those identified pixels are from those multiple perspectives, so I can determine where that is in three-dimensional space, and ultimately I can create a 3D point cloud. 3D point cloud is similar to LiDAR. You may have heard of LiDAR data, except this is not derived from a laser scanning process, it's derived from image analysis. Now, in a geospatial context, if you want to improve the accuracy of the output, you can apply what are called ground control points. Those ground control points will tie the images into specific known coordinates, three-dimensional coordinates, x, y, and height. It basically requires you to know the coordinates of identifiable features in your images. And based on that, again, you can improve the geospatial accuracy of the model. So for the rest of my presentation, we're going to take a look at structure from motion in action. So for this simulation, I'm going to use a piece of software called Global Mapper. There's a component of Global Mapper that will let us process those images, and you'll see that in just a second. Just for visual reference here, we have some imagery. This is a kind of low resolution image just showing our target area. You'll see a little farm here. I've already loaded the images themselves. These are the drone collected images, which are represented by little icons on the screen, of which there are 148. I can select one of those. I can identify it's a coverage area. You'll see that little polygon. That's how much physical area has been covered, and you'll see a visual representation of that in this preview window as well. If I choose another one, you can see the building here, for instance. This gives us an idea of the target area and the coverage. Now, the actual tool I'm going to use for this process is what's referred to as pixels to points. It is a component of the software that allows us to load our images. I'm just going to load all of those picture points that I had displayed on my screen. Eventually it will populate this table view, and again we'll see a preview on the adjacent images. This is all of my images. You can notice the latitude, longitude, and elevation of each of those. If I select one, I get a close-up view of that area. I can zoom in a little closer. If I had been using ground control, as I mentioned previously, I could identify where those ground control points are. Maybe it's a target painted on the ground, or maybe it's something that's physically visible on the ground that has been surveyed, and I can attach coordinates to those identifiable features. Also worth noting here is the overlapping nature of my photographs. You're seeing the side of the building here. If I choose an adjacent image, you'll see the same building from a slightly offset perspective. And that is the basis of how this procedure works. Because if I actually did go through and hit the run button, the process would analyze each picture, look for what it sees in each picture in terms of the pixels, literally colors, or array of colored pixels, and look for other images that have something similar. It would then perform that triangulation process I mentioned before. I could apply certain settings based on my camera and determine what it is I will actually want to generate. I'm going to show you these output files in just a second. Now, if I actually ran this process, it would take better part of an hour, maybe even over an hour, depending on the hardware, depending on the capability of my machine. I'm obviously not going to do that. I'm going to close the window, and a little bit like a cooking show, I'm going to show you one that I had previously prepared. Let me turn off the base image, or also turn off the images, and I'll show you the output. First of all, worth noting here, there's a few different files. First one I'm showing is what's called an Ortho Image. This is essentially a stitched together view of that the array of images. It's one large image. A few gaps in here just simply based on how the data was processed. There were shadows here. We weren't seeing any data in our photographs, any overlapping data. So there's a few holes. We also, as a byproduct of this process, generate what's called a mesh. Now, the mesh initially will look like the image, except this is a special view because this is actually a three-dimensional model. And you're hopefully seeing that on my screen right now. This, I like to remind you, was generated from simple top-down images. The analysis of those images was able to recreate this scene in 3 dimensions. You can see quite clearly the building here, you can see the trees, and you can start to see a little bit of the lay of the land. We can get right down here and look along the road. This is a byproduct of that process, of that structure from motion process. Let me close that window and show you a couple of other things that were generated here. There is what's called the point cloud. Now, this is the basis for all of the other data sets. This, it looks like a solid surface, but it's actually a series of closely spaced points. This again is a 3D data set. These are 3-dimensional points. If I popped up the 3D view again, they would appear in 3-dimensional space. Also, because they have information associated with them, we can change how they're displayed. We can look at them based on a height value. How high are they above the ground, for instance? So there's different ways of displaying these. We can also identify within this point cloud which of the points are ground, and that's what I've done here. So these brown points are the ground points. The gray are the non-ground buildings, trees, etc. And from this data, we can run through a process of what we refer to as gridding, which ultimately generates a terrain model. The terrain model forms the basis of a lot of different analysis procedures, including, for my final illustration here, some contours. We're able to generate some contour lines from our 3D model, from the model that we generated from the images. Now, that was a quick run through of some of the files we can generate using this process, but I have to remind you, where we started was simply top-down, overlapping, simple images. Now, that was a very hasty illustration of the process of structure from motion. If you have a questions, you want some more information, please feel free to send an email to my colleagues at geohelp@bluemarblegeo.com. Our technical crew would be more than happy to answer your questions. Thank you for watching, and hopefully you find this useful.